Alright, hello everyone. So in this one we're going to talk about key points, key point extraction, descriptors and so on. So why talk about those? Let's have a quick recap. Alright, so again the VSLAM was working like this, that like we have a bunch of obstacles in the field, right? We observe it, this is bird's eye view from the top, and then let's say we see those key points over here, right? So in the picture it looks something like this, and then we move a little bit and now our image looks something like this perhaps, right? Something like this. And then how do we know that, like, you know, this is the same? So this one over here, I'm guessing that's the one. Like, how do we know that those are the same, right? So this is when we do tracking, right? So we compare the positions of the key points in time, right? How do we know those are the same? And then during keyframe estimation, when we compare the images from the left eye and the right eye, right? So it looks something like this. Like, how do we know that sorry, like, how do we know that this is this? How do we know this is this? Great question. Key point extraction and feature descriptors. So, long story short, just like in super short summary, people do it in this way. We look for given image, right? We do it for both two images that we compare, either left eye in time, as here, or left eye, right eye. So for each of the image, we run visually through the pixels and we look for corners here, 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 but also probably here and here, and here and here. So this thing over here, right, like where the triangle meets the horizon, is also a corner, kind of, right? This thing over here, just visually, right? So yeah, we're just, so those would be like kind of like false positives, because it's not a point in space. But yeah, we'll just worry about this. We'll just worry about this later. So first thing, we look for corners. How do we look for corners? I will show you slightly more detail in a second, but like basically we take a circle and then we compare, like if there's like a couple of pixels, but more than one, that are really different contrast than the rest of the things on the in the circle, that's probably corner. And the circles maybe is pixels, maybe like 12 pixels or something, right? So this is how we find corners. And then for each corner we compute a descriptor, and that's really heuristic, and there's many different descriptors, but like what really works is you take sort of, let's say here's the center point, and then you take literally random, like a bunch of random, I mean probably it's not 100% truly random, but like it's what it feels to me as random differences of brightness in pixels. So let's say this and this pixel, like A and B, and like, so you take like a descriptor of length 32, let's say, and then you compare, okay, is point here brighter than P? If yes, then I put 1. Otherwise I would have put 0, but because it is, I put 1. So I put 1. And then there's like a bunch of like this and this, this and this. It can be other way around, right? It can be like this and this, or like this and this. well, usually as far as I remember, it's like in a straight line, right? And then you just compare, and like you do it for 32, and then you have like 0, 0, 1, something like this, like a type of descriptor, and then it's kind of like a visual hash. That's how I think about it, visual hash. And then, so let's say that let's come back to this picture over here. Actually, can I like copy it? Let's do something fancy. Can I do this and copy? It's not like it's very pretty, but I want to learn copying. Yes, I can. That's pretty cool. But I cannot really paste it. Okay. Forget it. I will figure it out later. This, yeah, okay. Painting is on. So left eye and right eye, right? So let's do this and this. Left eye, right eye, and so I have, and then let's draw like horizon. And so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I have 5 descriptors for this one. Let's say it's like 1011, 0111, 0001, and so on. And then here I have 1010, 0111, 0001. Then we'll do like a, so let's call it 1, 2, 3, and then up to 5. 1, 2, 3, and then up to 5, right? And then we take like a matrix. I doubt it's in reality it's like a matrix, but that I will just explain it this way. 1, 2, 3, 4, 5, and then actually maybe here's like, I don't know, maybe there was like a bug and there's like a 6 one, you know, so it's like it could be 6 easy, right? It doesn't have to be square, that's what I'm trying to say. And then I take this one and this one, and then I compare them element wise, and I count number of times they are different. So 1011 and 1010, they are only different here, so the distance between them is 1. This is called Hamming distance. So awesome person, by the way. Amazing lecture. You enjoy your work. You should, if you don't know it, you should watch it. It's like life changing, you know. But anyway, so this is efficient because like we can actually XOR it, right, and sum of XORs. So XOR is 0, 0, 0, 1. So sum of XORs is very, you could implement it in a really efficient way. And then you just like compute distances. Let's say like 1 and 2, right? I could let's compute the distance between 0, 1, 1, 1, and then 1, 0, 1, 0. So that's like 1, 1, 0, 1. So that's 3. Distance is 3, right? And then we do this, and then like we basically go one by one and just brute force match the ones that have closest distance. So the feature or the key point with the descriptor 1010 in our example would be matched to this one, right? And then what just happens in practice is that they match up, and that's it. It's so we will have false matches. It's just like a matter of fact. I think why it was done this way is because all of this stuff is very heavily parallelizable, so you can really make it fast with using parallel computation, and then it's simple and it just kept working, you know. So this style of features is called ORP. I will just show a paper. There's in a second. There's also stuff that's called SIFT. So this is like a feature descriptor. It's slower. Other classic descriptors for features, but those are more like image features, not really like key point features, but you could also, if you really wanted, use those, right? But it would be kind of hacking. It's like histogram of oriented gradients. It's a kind of a common one, but yeah. Anyway, this is like yeah, this is kind of different word. Maybe I shouldn't even really mention it. And then what? Oh yeah. So there's a really lot of like neural network based feature descriptors those days. Yeah, but yeah, still ORP is like in just classic SLAM. You have stuff like what's the name of it? Like ORP SLAM. Oh yeah, ORP SLAM free. This stuff is state of the art, I would say, in the classical VSLAM, to the best of my knowledge. So yeah. So again, detect the key points, compute the features. So if I go like there's a paper that introduced it. Let's see. Can I like see it or something? I think I've seen on Wikipedia that there's like okay, oriented fast and oriented brief. So here you go. Fast, robust, local feature detector. That's fast. And then fast key point detector. And then brief. Binary, robust, independent, elementary features, which is just like, you know, sum of visual yeah, whatever. It's like a product. It's a product of this binary differences with funny orientations. So yeah, fast. Here's the circle, and then one of two conditions has to hold. A set of n contiguous pixels S from the circle has intensity higher than IP per threshold or IX APT. So intensity of, for each X, there's the intensity is higher than the middle pixel plus some threshold T. So there has to be a set, and this set is like size of this set has to be bigger than some number, right? So if this is like and we do this thing for like every single pixel in the image, right? So like there's a tricky way to, or like probably it's hard to say, but there's like a good way to quickly compute this iterating over all pixels in a really fast way, like not recomputing everything all the time. And then like of course you could just parallelize it, and then it's like really fast on like GPU or something. So if for example 1, 2, 3, 4, 5, 6, 7, 8 and like up to 12, here's like this contiguous set of pixels, it's like brighter by a threshold of T than this candidate pixel in the middle, then that's like a good thing. And then or like a dark corner, so like inverse of this. And this is how we like will truly do this for every single pixel. And then like the parameter is like yeah, we have like fast, speed and whatnot, and using magic people have chosen n equals 12. But there's also like machine learning approaches, but yeah, right. N equals 12 is the magic number, very important information. And the brief. Do we have this somewhere? Like, oh yeah, here we go. So here's like our middle pixel. And then we compare. So those lines are like what we actually compare. This with this, this with this, this with this, this with this. It's kind of like random, honestly, right? But like it works, so why not? All right, yeah. Let's just like look at the So if this pixel intensity is higher than this, then all the patch of pixels, yeah. and yeah, then we like encode this as a bit string. Different approaches to choosing test locations, yeah. Alright. Then yeah, they make like a bunch of comparisons, blah blah blah, research. But yeah, pretty easy stuff, and it worked. So check out. If you go to my repo, GitHub, Ghostface Killa VSLAM, and you go to lessons, extract and match features. This depends on like local recording of the data that you generate. It's in the README as well, but you can generate it with this. So you generate some data, you put in your like data dir or like recording name here, then you run it. So let me run it for you. Wait. Oh yeah, this one. So here's visualization. So this visualization, like left eye and right eye, it should be familiar, look familiar to you. So we just looked at how I actually render those, and then now you might suspect why I have chosen triangles, and like how triangles are really convenient to work with for this particular project. And then this is left eye and right eye. Notice how indeed in the left eye the violet triangle is kind of to the right, and vice versa. Notice like a tiny little bug in our rendering. This should be violet all the way, but it's not. So, and each of those, so now we're going to iterate over sequence of matches that were computed just as we have described, and so we have like Euclidean distance between those. So if we were to overlay those x's, right, on one image, the distance between those would be 20 pixels away. And then we look at this Hamming distance, so how much do the descriptors differ, right? And here's like a super zoom in of those, and like you can see that we have really a lot of features over there, right? And yeah, we could also do some kind of like feature sparsification and choosing like the best match and whatnot, but I just wanted to do like the simplest thing. And then like when you touch any button apart from escape key, you will iterate over matches. So we will just like go through matches in order of descending Hamming distance, right? So number 1, number 2, and Hamming distance is 2. Number 3, Hamming distance is 3. But yeah, looks like a great match. Those are the same, and one more, and so on. And we iterate and iterate and iterate. And you can see that like in general, when the Hamming distance is low, the features seem to match pretty well. And then let's just look at some further. I think I actually put in some filtering on Hamming distance. And yeah, you can also see like how this thing is probably further away, because like the or closer to us, because like the Euclidean distance is further, right? So it's like as it comes to us, like it's sort of closer to that. It's like things that are in the distance, both eyes are going to be seeing those in more or less the same place in the image, right? So this thing seems to be way closer to us because the Euclidean distance is wider. Like as the Hamming distance goes further, and descriptors really start. So like the descriptor length is 32, right? So if Hamming distance is 22, it means that it's only the descriptor is only similar in 10 places. So that's pretty rough, and probably not a great quality match. So we see this is not actually the same feature. We don't. Yeah, it's just like this is like the edge of this triangle probably, right? Just looking with the human eyes. So you could see how machine learning could be used to filter out this information. But yeah, here's like another feature which is like having distance 22, but still like it does provide some information, right? So yeah, it might be nice to just leave them in, and oh, here's another one, right? And like it's spot on, right? I mean, maybe not spot on because this is like tip of the triangle, but it's pretty good match, although it's high homing distance, right? So it's, this one is only similar at 9 bits, right? So only 9 of those differences are similar, but still it's worth keeping those in. And then if the matches are wrong, we just reject them later at the stage of optimization. So yeah, this is how key point extraction works, more or less. And then like you could read the code. So it's pretty simple, right? So yeah, we just read a bunch of data. We do like this feature debugger, which is this like plot maker, and then we detect and match binocular. So we want this from the orb-based feature matcher. And then let's see, what is this? So we say self-detect and then self-match. And then, okay, what is self-detect? Self-detect is you ask orb feature detector to detect and compute. And this, as far as I remember, is directly from CV2. Yeah. So this is detect, key points, and compute feature descriptors. And we wrap them into my custom, like same as always, like structured data structure, structured data structure. Terrible way to say it, but whatever. And then here's like a matcher. So row CV matches, self feature matcher, and as far as I remember, this is BF, so brute force matcher, which just literally computes brute force in the sense that it literally computes all pairwise distances, right? So it's supposedly slow, but yeah, that's what people use in practice. Maybe use some kind of bit tricks to make it fast. And yeah, this feature match, right? It has this nice like pixel and homing distance thing. Yeah, and pretty much that's it. That's what it does. So and you need to practice this, right? So if you don't actually practice this, it sounds very easy, but if I were you, I would just rebuild it from scratch. Otherwise you won't be able to understand it. And then the way to practice this, I would do kitty dataset. So there's this by some awesome forks, right? And then there's like this like stereo vision thing, or like depth or like odometry thing, right? And it has there's like a data set of the images, and then there's like left and right, and there's like extrinsics and intrinsics saved into their data, and then you can just like load it and then match it up. Then actually I think somewhere in my over here there's still like a feature match or something. Let me see. Yeah, exactly, right? So I did this, and you can see how it's kind of like going slow, right? But like how the feature match works in general, and then how you can, I think I did like some like depth estimation or something, such that yeah, the deeper points are more blue and the brighter points are more red, and you can see that it does work, right? Sometimes it gives you like weird results like here, right? Or you have these high differences when there's just some noise in this like feature matching, right? And like if you make a difference of, if you make an error of like a couple of pixels, it means big error for estimation, for depth estimation. We'll see why exactly, because like this triangle geometry is kind of tricky. But yeah, overall it works, and like if you have a lot of points, and then you can offset, like you on any given object, if you have many points, you can sort of offset the errors with each other. So it all works. And yeah, that's it pretty much in this one. Probably next one is like depth estimation, stereo depth estimation. Yeah.